Oh, today I'm going to go over 7.1, 7.2, and 7.3, but this video is just 7.1. I don't have an extra copy of the book, so I'm just going to go what I had written, and so you could pause if you need to write stuff. So graphing exponential functions. An exponential function, if you remember, we have either growth, oh, no, this is the first lesson. Okay, we do either growth or decay. So an exponential function means that we have a number and an x as an exponent. So I'm going to write a, but usually we have b to the x, okay? There could be two types of functions. We have either growth or decay. Growth looks like this, starts off, goes up. I guess I'm going to write with blue. Decay starts off high and goes down. Both of them have an asymptote, and it's y equals 0 because it gets really close to the x-axis, but it never equals 0. Why is that? Because no matter what number I put, I will not equal 0. 2 to the 10, of course, is a really big number. But if I go negative, 2 to the negative 1, that's 1/2. 2 to the negative 3, that's 1/8. So it starts getting smaller and smaller, and I can never get 2 to the x will never be 0. Okay? The other things are the growth and decay factor, by how much it's growing or decaying, and we'll go over the difference with that and a rate. So an exponential function is b to the x. Usually we have a and then b to the x. A is your starting amount, and b is either your growth or decay factor. If this is greater than 1, it is growth. Because everything starts off at 100%, so when we are over that, that's growth. That's more than the 100%. This one, if this is 3, it triples every time, and it's 300%, but our growth rate, it's not factor. 3 is our factor. Our rate is 2, or 200%. Okay, let's look at one. First, this is like your first examples in the assignment. Here is exponential growth. This is 2 to the x. Maybe that's why I use that for my example above. But anytime this number is more than 1, it's basically this graph. This one has no transformations because it's just 2 to the x. Now there's the graph. You could also think of the table. It doubles every time. 0.25 times 2, 0.5 times 2, 1 times 2, 2 times 2, 4 times 2. Okay? The asymptote right here is y equals 0 because it does not ever equal that. And I gave you those examples above. So whenever you have growth without any transformations, your domain are all numbers because there's arrows on both sides getting wider. Our range is just above 0, not equal to 0. Y equals 0 is the x-axis, and that's our asymptote. So our y-intercept is 1, so it's always 0, 1. Why? Because anything to the 0 is 1, so if you put 0 where the x is. The only thing are the ends. The right end obviously goes up to infinity, but the left end is going closer and closer, approaching 0, even though it never equals 0. So this is always the same, this information for exponential growth, unless there are transformations, which we are getting into right now. So here's transformations. Here's our general formula. A and B multiply. This is considered inside. Inside affects left and right. Outside affects up and down. A and B multiply. If the number is bigger than 1, it's going to get narrow. If it is between 0 and 1, it's going to get wider. That's where I say if I'm twice as tall or I'm 1/2 as tall. The negative here reflects around the x. If you had a negative here, it reflects around the y. So here is this one with 1, 2, 3, 4 transformations. This is your parent. That is your parent function. Exponential always have a base of a number and an x in the exponent. So the 4 transformations, negative 1/2 does 2. It reflects it and compresses it by 1/2, which makes it wider. Here's the graph. Negative 4. So see, our standard is a negative h, so h is a plus 4. It shows plus 4 here. Our h is a negative 4. In order to get a plus here, and our standard is negative, the inside is opposite of what you think. So negative 4, which is left, and you can see the graph move left, and 1 for k, which moved it up. But it's hard to tell because it moved, well, it did, because usually your graph goes like this through 1 and then goes up. So you could tell this one did move up 1. So your asymptote for this one is y equals 1. Your asymptote for the parent is y equals 0. Okay, this one is growth. I could tell because we read graphs left to right. Usually it goes through 0, 1, but this one is down 2. So it has gone 2 units down, so k is a negative 2. So if this is our parent, we write our parent minus 2. That's our k. K is outside the function. It's not inside over here with the function. All right, example 4, I always have a little fun. Oh, here is your rate is the percent that it's changing, but your factor, this is also true with decay, is 1 plus that rate. If it was decay, it'd be 1 minus that rate. So your starting number, 1 plus the rate to time. So this is what I was saying. I usually have a little fun with this and say Miss Temez, not Mr. Lopez, me, won the lottery. Suppose she takes a lump sum payment and she invests $50 million into an account that yields 5% annually. Graph the function and tell me the amount in 20 years. So I know you guys know how to graph, but I want you to understand where this equation comes from. Starting with 50 million. Now we don't want to add all those zeros because reading a graph would be really hard in the millions. So we could just put 50 and we know we're dealing with millions. Our rate is 5%. So it's 1 plus 5%. And remember, we don't put percents in our formulas. We put divide by 100. And then time is here. So this one says how much money in 20 years. You could do this in a calculator. You could do this in a calculator. But either way, it's going to be 132 million in 20 years. They graphed it. And you could graph the equation y equals this and y equals 20 and see where they intersect. This would be an x. And see where they intersect. It'd be 132 million. 132.6 million, maybe 7.7. Okay, 7-1. Here is another person saving. First day, January, she saved $1. Increases by 1%, 0.01 a day. How much will she have in day 80? So our growth factor is our factor is 1.01. Our rate is 1%. Okay, that's our factor, which goes in here. We're starting with $1, but that really doesn't change anything because multiplying by 1 no matter what it is, and then put 180 in the calculator, and I think you get 0.5997 or something like that, which is $6 after 180 days, which is 6 months. So know how to put, this is 180, know how to put this in the calculator. Now we're going to talk about decay. Decay is a little confusing. Well, let me talk about it. It's when your rate is between 0 and 1. So decaying by 50%, 0.5. Decaying by 25%, 0.25. But that's the amount of decay, your rate. Your factor is 1 minus that. So I always tell people to think about how much is left. That's what goes into the equation. So 15% decay, 0.85 is left. Okay? If you had 25% decay, it'd be 1 minus 0.25 or 75% left. Okay? Whatever is left. So we went through this table. 5 is growth because it's greater than 1. Our rate is growth by 400%. Sorry, a couple classes I was wrong with these between factor and rate. Our rate is 5/7. This is decay because it's less than 1. Of course, we can't have a negative base for exponential, so it's just between 0 and 1. So to get to 1 is 5/7, so that's my rate. 4/3 is more than 1. It's 1/3 rate. 1/3 rate is about 33%. 5% growth, this is my lottery winnings, so my rate is 5%. And 0.85, which my example is up there, maybe I wrote that after I wrote this, it is decay, and it is 15% decay. All right. Example 6, we start getting into decay. And like the growth one, it pretty much is the same for everything that has decay. So this number is between, your base is between 0 and 1, because we never have a base of 1 because that doesn't really change anything, and we don't have a base of 0 because that is nothing. So between 0 and 1, any fraction, any decimal between there. So all real numbers are your domain because of these arrows. Your range is above the x. This is my asymptote, y equals 0. My y-intercept is 0, 1 right here. Why? Because this is 1/2 to the 0 equals 1. Anything to the 0 is 1. And behavior, this is where it's kind of reflected around the y compared to growth. And behavior is that the left side goes off to infinity and the right side is approaching 0. All right, is that it? No, I think there's one more, example 7. So example 7. Example 7 is a transformation. Yay, I'm going to get a different pen because I'm able to write in this. I guess I didn't do it in class. So our parent is 1/4 x. It tells us there's one transformation, and that -2 counts for 2. Well, you can see from the graph, usually exponentials up here, this is reflected. So -2 reflects on the x-axis. And 2, it's stretched by 2. What does that mean? It's vertical. So if I stretch my height twice as tall without gaining weight, I'm going to get narrow. And if we were to graph, well, it's reflected. It's hard to tell. But if we were to graph this one's going to be like pulled in a little closer than the parent. H, remember, it's x minus h in the formula, so that's a minus, so my h is just 4 plus 4, which is 4 units right. Plus 4 for horizontal is right. And k is a plus 3, so 3 units up. K is not opposite. It's this stuff right here inside, which is opposite than what you think. And that is it for these. So your assignment was this, no graphs. What does that mean? That means for these first ones, you just follow example 1 and tell us the domain, range, y-intercept, asymptote, that kind of thing. For example 2, it doesn't say it, but look at example 2 and tell me transformations. It's like example 2 and example 7. And then 11, 12, identify what k is. 14, 15 are exponential word problems. And 17 through 20 is like the table that you just tell me if it's growth or decay. All right, let me know if you have any questions.